Okay, for all of the different tip conditions, again, temperature distribution and the fin heat transfer rate. This chart for fin efficiency of a cylindrical fin. Then this table for fin efficiency and mainly fin efficiency of a whole bunch of different shapes of fins. So you will certainly not need all of that, especially all of the fin stuff. There's a whole bunch of stuff for a whole bunch of different shapes of fins. There aren't going to be 8 problems about fins on the exam, but you'll need something from kind of each of those sections. I'm just trying to kind of decrease, especially with some of these, with this page, decrease the amount of equations you have to copy onto your sheet. That said, there's not a whole ton of context to any of these equations. So you may still want to copy something like this to your equation sheet. Again, it's up to you. You'll be given this. The last part here, I have just some bullet points of things that I think you should have on your equation sheet, so you don't get to the exam and go, oh, garbage, I don't have that equation. And again, enough context in these equations that you know what the variables are and how to use them. So the basic laws: conduction, convection, radiation. Radiation is kind of the tricky one, because I may ask a radiation question that's doesn't fit neatly into a specific box, like a predefined equation from your book. So if you write down equations, know what they are and how to use them. Thermal resistance, there's going to be a thermal resistance thing. So I have the table for conduction, but not for convection. So know how to do that in the different geometries. Thermal resistance for a fin. So there could be a system where you have to have a thermal resistance value for a fin. Fin efficiency, fin effectiveness. The second to last bullet point is kind of a tricky one, right? Enough information that you can come up with boundary conditions. So it might be one of those, like kind of the 4 boundary conditions, the 4 common boundary conditions that we laid out. You'll probably have to come up with 1 or more of those at some point, but you may also have to come up with like a custom boundary condition that doesn't fit in one of those boxes, kind of more like what we had to do for the quiz. So it could be either or both of those. And then the information on the lumped capacitance model, like BO number, how temperature changes with time. So I said before, that's not going to be a major part, but there could be a problem, one of the short problems that's, I don't know, maybe like 15 or 30 points, something like that, on the lumped capacitance model. So could be one of the short ones. So hopefully this gives you quite a bit of information about what you're going to be given, what you need, and you can kind of have this up as you're starting to pull together all the different equations and whatnot. Because I know one of the things about heat transfer is like every special case has its own special equation, and that will continue to be the case. So a lot of it, this is practice, like how do we handle all of these different things. So there's quite a bit there. So I want you to, rather than just using your sheet for like writing down all the equations, I want you to be like putting context and how do I use different things? When should I use one or the other? Things like that. Okay, so you should have this. Hopefully it is helpful as you start putting together and thinking about the exam. I know it's still a week yet, but hopefully this is helpful. The other announcement thing, there is now on Moodle, and this is, I share this just for the sake of doing it. The next homework is posted. You see, it's due in 2 weeks. So it's due quite a while. But rather than waiting to post it, I thought I would post it. Then if you have a chance and you want to work on it, you're certainly welcome to do that. It's some of the problem, like this problem is not particularly hard, but there's a lot of stuff in it. I try to kind of guide you along. This problem especially, I'll talk a little bit about how we would solve this first problem today, but it's going to require a numerical solution because we won't actually be able to solve it exactly. So a lot of the stuff we're doing in class is looking at exact solutions at this point, but we're going to jump a little bit at least into numerical solutions. So we'll get a chance to practice that. A number of these problems are things that are like semi-infinite solid or somewhat similar things. So you are more than welcome, and a lot of them require plotting and graphing. So the spreadsheet that we made that I showed in class, this semi-infinite solid example, this spreadsheet is up on Moodle exactly for you to use it. So you still have to do some of the calculations and setting up the problem, but I'm not super interested in can you do all the parentheses in Excel correctly. So if this spreadsheet is helpful for the specific problem you're working on, please use it. Right? I mean, it's not all like, can you do everything from scratch? So take this stuff that's already there. You'll have to take it and modify it. You'll have to modify some of the values, exactly how it's used. But if this is helpful for solving it, which it will be for 2 or 3 of the problems, 4 of the problems, kind of take this and use this as a tool to help you solve those. Okay. The last, it's really one problem, but you re-solve the same. So the last little while, let me pull back up the homework. Just to show a little bit what I'm looking for. So the last problem 5 through 8, so it's 4 problems, but it's really just one problem where you're doing the same thing. It's looking at basically a piece of steel that's cooling down. And what we're going to do in this problem is look at it with all of our different models that we build up and see how they compare, where one is accurate, where one starts to break down, how the different assumptions that we kind of bake into them, how those actually play out in a problem and compare together. So this one is going to be a little bit challenge. It's going to take a little while. It might be a little bit challenging. So I just wanted to show you a little bit what I'm thinking for this problem. The actual, like when I solved this, the actual work I did on paper was pretty minimal. I think for 4 problems, it took me like a page and a half maybe, or a page. And I laid things out in quite a lot of detail. But there's quite a bit of work that you're going to have to do to like plot and compare and look at what these different models are spitting back to you. Try to get a little bit better feel for what they are and how they work and why we have different ones. So a lot of them, it's plotting temperature profiles in this cooling piece of steel, plotting them at different times. So you have to answer kind of a couple basic questions for it. And then we go through kind of 3 different models in 5, 6, and 7. Then in 8, it's just take all of the stuff that we did and put it on a single graph. So you should end up with something. I just did it in a single Excel spreadsheet so I could copy and paste stuff over, because a lot of all of the constants, a lot of the setup of the spreadsheet copies from one problem to another. It's just like the exact model. So I have a whole bunch of different spreadsheets with different models. And then, so here's problem 8. Looking at, okay, at a single time, let's compare the solutions from these different models. So we have the flat line is the lumped capacitance, and then we have two different other models, or I guess 3 different other models. So a lot of what I'm looking for in this problem is I'll be looking at the graphs more than like the work on the paper. So that's kind of where most of the problem is going to be. But try to, if you have problems setting this problem up or getting it working, I guess start it early enough that you can reach out for help on that. But obviously this is like 2 weeks away, so it's quite a while. Okay. In the meantime, I didn't pull up my notes. We are going to go back to a semi-infinite slab. So we talked last time about a single boundary condition. We talked really just about, well, okay, not a single one. We talked about this, we solved this top one, right? That's the equation we kind of solved and derived in class. And then I showed you this one down here for convection, surface convection, and said, okay, so if we have surface convection, we have this big ugly thing, and we looked a little bit, I had a pre-built spreadsheet that could solve it. The other equation, like another boundary condition we could expect, would be this middle one where we have a constant heat flux at the surface. Right, this would be a case where if you had like a large chunk of material and you slapped an electric heater on one side and turned the electric heater on. You don't need to write this whole thing down. It's in your book. You'll get it later if you ever need it. I don't think we actually ever will use this, at least you won't use it in the homework. You may use it on a future exam somewhere, but you'd be given it. So it's more just, I want to show they're all similar form. And a lot of the equations we're going to start running into, we're kind of, unfortunately, like our equation toolbox is proliferating. It is growing like bunnies. So a lot of it is not like, can you write down the equation and remember it? You won't remember. I can't remember any of these. But it's, can you identify the problem, do some of the basic analysis to figure out how can we think about this and model it, and then go and find, what tool you need from your toolbox. So that's what those, yeah, and just to, right, these are all going to be somewhere, they're all kind of together in chapter 5, which is where all of the stuff that we've been doing, the transient conduction stuff that we've been doing, is all chapter 5. Okay. So what we did last time was this problem, right? We had a little kid step on the beach. How long till you start crying? Or how long till I start crying? Right, here's a quote from Don May. It's just true. I don't know if that's a real quote, but I believe that Don May might be a real person. It's at least possibly a real quote. So this is a problem that we solved. We were looking at your foot when you step on a beach. We had gotten partway through this problem. So we had gotten to looking a little bit at what right, we said the first thing that happens is the surface temperature gets pinned at, all right, pinned in parentheses. Do you know what I mean by pinned? Like very quickly it gets stuck. It gets to a temperature at the interface between those two objects, and that temperature stays there. So the surface temperature is not changing with time. It very quickly reaches a temperature and then it stays constant. It's pinned at a weighted average temp. Right, and we looked at what that weighted average is. It was the surface temperature is the initial temperature times the square root of K rho Cp for body A plus the initial temperature times square root K rho Cp for object B, all over those two weighting factors, K rho Cp plus square root K rho Cp. Right, so that this equals just a constant value. So this is kind of an interesting observation, is that when you have two large objects that come into contact, the surface temperature between them very quickly reaches a steady state constant temperature. And that temperature only starts to change when the objects are no longer behaving like semi-infinite solids. So basically, as long as they're behaving like semi-infinite solids, this is constant. So I'll write that as kind of the qualification. Okay, and we got this because we knew that right, the heat flowing into the cold object must be exactly equal and opposite to the heat flowing out of the hot object, because heat flows out of the hot into the cold. So we got it from just a simple energy balance like that, but we get this kind of interesting result. For our foot, this weighting factor, K rho Cp, of your foot, which I believe we called object A, right, we would plug in the thermal property data that we have. We would get 774 joules per meter squared Kelvin second to the second to the 1/2. I think that's right. And then for K rho Cp for the sand, object B is 572 joules per meter squared Kelvin second to the 1/2. So you get kind of this weird group of units, which is fine because we're using the same units on the top of our equation and on the bottom. So we don't necessarily have to get these into a special kind of unit so long as they're in the same unit system. Then our surface temperature, TS, would be our initial foot temperature, which is 37 C, times that weighting factor, 774 joules per meter squared Kelvin second to the 1/2. I'm going to stop writing units because that's a lot of units. And they're all going to be the same, plus 60, which was the sand temperature, times its weight, 572, divided by 774 plus 572. So this tells us kind of right away what the surface temperature of your skin is going to be when you step on the sand. It's going to be about 47 degrees, which is hot, but not super crazy, right? Anybody know, like, it's over 100 Fahrenheit, but not wildly so. Like, there are places in the world that get to be this temperature outside. So it's very hot, but it's not unreasonably so. So it's weighted, it's not a direct average of 37 and 60. It's weighted a little bit closer toward your foot temperature because your foot has kind of a little bit, right? It's higher thermal conductivity and heat goes to the surface a little faster. So it kind of wins the battle. It's a little bit a higher weight in the relationship. Then we can solve for T for how temperature is changing in space and time in A or B, right, in the sand or your foot, with the T minus TS over T initial minus TS equals ERF of X square root 4 alpha T. Okay, so if you want to figure out the surface temperature, you could do that really easily with this kind of weighted average. If you want to figure out the temperature somewhere in the object, so right, if you are burning yourself, if you're this little kid and you step onto the beach, you don't actually start to feel when the very surface of your skin raises temperature. You start to feel it when that temperature a little ways inside of your foot where you actually have nerve endings, when that temperature starts to go up. So if you're the little kid, you start to cry. You start to cry when like T of 1 millimeter reaches some temperature. So we'll say about 40 degrees Celsius. When you've really had at least a little bit of a temperature change a little ways into your actual foot, that's when you start to feel it. That's when it starts to actually hurt. So how long does that take? Then you could plug in all of those values. So you'd have 40C minus 46.8C divided by 37 minus 46.8. That'd be the error function. So you'd plug in your value of X that we happen to be looking for, 1 millimeter, 1 times 10 to the minus 3 meters. And then it'd be the square root of 4 times alpha, which is 1.5 times 10 to the minus 7 meters squared per second squared times T. That's all under the square root. And then you would take this and solve for T. In a lot of these kind of problems, you can't, and it's not worth going through the hassle of actually like trying to solve this analytically, like figure out a T equals equation. So a lot of times we can just solve these kinds of things numerically with like Excel, MathCAD, MATLAB, some program like that. So when I solved this, I used Excel and used the Excel solver function. Does everybody know what Excel solver is? Raise your hand if you know what solver is in Excel. Raise your hand if you've never heard of that. Okay, so everybody's at least heard of it. Okay, so if you use Solver, then you get that the temperature or the time is about 3 seconds. So it takes about 3 seconds for the temperature a millimeter into your foot to go from 37 up to 40. Just to get like kind of a visual picture of what happens, because I think it's helpful for to see it. No, that one. I think this is a good image to help you see a little bit what's happening. So initially you're at, this is your, let me get a different color because that's all red too. So this is your initial temperature TA. So that's, I don't know, maybe the sand temperature. This is your foot temperature. They initially come together and they get this temperature here right in the middle gets pinned right there, and that gets stuck. Then the heat starts flowing from the hot thing to the cold thing, which is what causes this decrease in temp here and an increase in temp there. So you get kind of these curvy lines. And eventually, right, what we're doing is, okay, so the surface temperature is pinned right there. What we were doing is watching, like, you know, right here, say, and watching for 40 degrees C and saying, how long does it take for this heat? You know, initially it's kind of, it looks like this and then like this. How long does it take for the temperature there to actually like kind of build up to 40 Celsius? But you start, yeah, you kind of get this this type of a shake, and that kind of flattens out over time as more heat is going from the hot object to the cold object. So you can also see initially, like we get a lot of heat transfer because there's a really steep temperature difference between the two objects. But as time goes on, that kind of flattens out and there's less heat flowing between the two objects because this, the slope here, which is related to conduction, that slope decreases with time. So heat transfer starts to slow down. But kind of throughout the whole process, as long as we're semi-infinite, we get a pinned surface temperature. So you won't have any temperatures in your foot ever until like things are really bad, until some of those assumptions break down. You'll never have temperatures in your foot over 46.8. Like it can't go above that because that's the highest temperature. That's the surface temperature. So, okay, we so far have kind of lived in this world of extremes. So we have two different models. I think they're useful conceptually to think about what's happening. They're useful for modeling systems in certain situations, but they live in kind of two separate extremes. One is an extreme of infinitely thin, right? If the object is infinitely thin, then it all changes temperature at once. We can use the BO number to see if it is infinitely thin or not. But then it's a flat temperature profile inside of the object, and the object all changes temperature together. The other is if it's infinitely thick, and then we have kind of the temperature or heat transfer kind of like moves slowly in and causes like the temperature to be looking sort of exponential-ish. But you get kind of this swoop that keeps growing and growing and growing into the object. Those are two useful extremes, but obviously a lot of things happen in the middle. So what do we do? What do we do with a medium-sized object? So this is one that would be not infinitely thin. Not infinitely thick. Okay. Then what do we do with it? These two infinite, the lumped capacitance model and the semi-infinite solid, those are the, in some ways, the most straightforward. So if it's not infinitely thin, that means that the BO number is greater than 0.1. Right, that's our qualification for infinitely thin. Infinitely thick is the Fourier number greater than about 0.2. Okay, so those are kind of the two, these are two groups of variables that we can use as kind of a check for, are those assumptions breaking down? So if those assumptions are breaking down, then we have to go back to the heat diffusion equation. Because the heat diffusion equation, we didn't have to make all of these assumptions. That's where all of these things kind of grew from initially. So if we have an object like this of thickness 2L and initial temperature that's flat, so an initial temperature in the object, so it's some thickness, it's a plane. So this is a 2D plane. We'll call this the X direction. And on either side of our object, we have convection. Right, our little fluffy cloud of convection. On either side. So with, if it's not infinitely thick, it's not infinitely thin. We can still model it with our heat diffusion equation because that doesn't have those same kind of assumptions baked into it. So we would have our 1D conduction model to be d squared t dx squared equals 1 over alpha partial t partial time. So when you're writing this in your notes, the d's are not normal d's. They're the little funky looking d's because it's a partial derivative. Because temperature is changing not with just a single variable, it's changing with two variables. It's changing with both time and space. So that's why we get a partial derivative, and that's why we haven't wanted to jump into this and solve it right away, because we don't have a normal differential, we have this partial differential, and we can't use a special trick like we did in the semi-infinite solid where we used the similarity solution and changed it from a partial derivative to a normal derivative. We actually have to deal with the partial derivative. Okay, so that would be our 1D conduction model. We would need two boundary conditions and an initial condition. So we need one for each of the things. So we have its first order in time. So we need one thing for that, an initial condition. And it's second order in space. So we need two boundary conditions for that. Our initial condition right? And this should look really familiar from the homework, hopefully. Our initial condition would be T of X and 0 equals the initial temperature. So that the temperature at any point is just the initial temperature, a flat initial temperature like I drew. Our boundary conditions, there's going to be a boundary condition at the middle, which is from symmetry, that there has to be either a max or a min temperature at the center. That's where the maximum temp is going to be. That's where the min temp is going to be. The derivative has to be 0. The second boundary condition is at the surface, and that's the convection boundary condition. HT, T of L and T, so T of the surface minus T infinity, right? All this is T surface, but it's a function of time, because the surface temperature in this is not going to be constant. Okay, and then I'm going to skip over a number of steps that you guys had a chance to see functionally how they work. We're going to skip over some of them to the answer, but we're going to do these equations model any problem. Right now, they model all of the problems like this. It doesn't matter whether it's infinitely thin or infinitely thick or in the middle or anything. It doesn't matter whether it's you know, a piece of metal or the best insulator. It doesn't matter. It models all of these different problems. Slow conduction, fast conduction, high temperatures, low temperatures, anything. Right, alpha, T, X, L, K, all of these things are going to be changing for every single problem. The interesting insight is that they don't all matter individually. They matter as specific groups. And you can take specific groups of these variables and look only at those specific groups. So that's what we're going to do, is we're going to take this and do what's called non-dimensionalization. We're going to basically take all the units out of it as much as we can. Then we can solve it once, get the answer, and then we just solved it for every problem that's like this. And the only thing that we actually have to do is then put the units back in. So we're going to take all the units out, solve the math. And the beautiful thing about that is we can go, well, math people have already solved it, so there's the answer. You just write it down. And then all we have to do is put the units back in afterward for whatever specific problem we're looking at. So that's kind of the motivation for doing this, is we don't have to solve this from the start for every single problem. We just have to be able to figure out how to put the units back in because we already have the answer. Okay, so you go into this a little bit in detail in the homework, but we define some new variables, which we put a little star by them. Those star variables are non-dimensional variables. Right, they're non-dimensional, they're unitless. So they're not metric or English units, they don't have any units. So we define a non-dimensional position in our thing, which is like a percent from 0% at the center to 100% at the surface. So we're like, what percent of the way are you toward the surface? So that is X over L. We define a non-dimensional time, which is alpha T over L squared. That's the Fourier number, which we've looked at before, so they're the same thing. I'm writing it as T star just kind of for consistency because we're doing all of these as star variables. And then we define theta star, which is equal to theta over theta I. So again, I think you can think of these as like the percent. We'll see the non-dimensional time isn't a percent, like it doesn't go from 0 to 100%, or from 0 to 1, it goes to kind of whatever value. It can go up to like 100. So that's the one that doesn't go from 0 to 1. But X star and theta star both go from 0 to 1, where 0 is like the center for X. For theta star, 0 is the initial temperature. No, okay, so 1 is the initial temperature and 0 is the final temperature. That's right. So when everything gets to be T infinity, that's 0. But it starts initially at the initial temperature, 1. Okay, so what this does is, again, you kind of see hopefully a little bit like how the actual calculus works. It works because differentials are linear operators. So like you can take constants and put them in and take them out. So we basically just plug these constants in. We just kind of have extra constants hanging around. Plug those into the differential, pull them out, cancel out as many constants as we can, and we get a much simpler equation. So then, and again, you hopefully had a chance to look at this. Equals d theta star dt star. So instead of having a differential equation that has like temperature values and position values and alpha and time values, all of these different units from our problem, it doesn't have any of those. It's all these dimensionless variables. So that's our governing differential equation. Our initial condition becomes theta star at x star and 0 equals 1. Our boundary conditions become d theta star dx star at x star equals 0 equals 0. So that one doesn't really simplify, but it does take the temperature and position units out. And our second boundary condition is d theta star dx star evaluated at x star equals 1 equals minus the BO number times theta star. So really the only thing with any that's not like a unitless number or a dimensionless number, it is a dimensionless number, it's the BO number. That's like the only thing that pops up is another dimensionless group. So we don't have any length and width and temperature in any of these kind of units, heat capacity, like none of those things are in here. This is just like boiling it down to the basic math equation, right? An equation that you might solve in multi. And that's nice because people have solved it. This is always the easiest way to solve calculus problems is find calculus problems that people have solved and look up the answer, right? We agree? Okay. So, so what's the answer for this one? Okay, it's not going to be quite that easy, but let's think about it. So it's going to have to vary with right, theta, theta star equals some function. It has to be a function, right? That's our temperature. it has to be a function of position and time, right? It has to be changing with both space and time. What if those two things were separable, right? Like, what if this equaled, well, let me write it, is f, some function f of x, so of position, and then another function g is true. So we're going to just say, what if this were the case, right? We don't have, it doesn't depend on position and time together. These are kind of two somewhat independent parts, right? It has to depend on both position and time. But what if they're separable? It depends on one function of position and one function of time. So we would then plug that back into our differential equation. So our differential equation, we have two parts. So d theta star dt star. That would be equal to, well, f of x, that's going to be constant in t, so we would pull that out of the integral. So this would be f of x star, because that gets pulled out of the integral, times the time derivative of g. So it would be g prime t star. We can do the same thing, same idea. D x star squared. Now g is going to be able to pull out of the integral, and we're going to get the second derivative of f. So it'll be f double prime x star times g of t star. Okay, so we've kind of put these together. And we would get that f, I'll write it f g prime equals f double prime g. Again, we can separate those out. So f divided by f double prime divided by f equals g prime over g. So if this is true, and it is because somebody else has already shown that it's true before, if this is true, what has to be true about this equation? It has to be like that ratio f double prime over f has to be a constant, just like an ordinary number, and the ratio g prime over g, right? F depends on position, g depends on time. So the ratio on each side, they both have to equal just ordinary constants, and they have to equal the same ordinary constant because they're equal to each other, right? So the time and the like t and x both have to all cancel out perfectly, and we just have to be left with a constant. Okay, so if this is true, then those two things must both be equal constants. So what does that mean? What does it mean practically? It means f double prime divided by f equals a constant. So the second derivative must give back the same function but we could have constants out in front. So okay, so if we have a function f, we take the derivative twice, it has to give back the exact same function with maybe some extra constants out in front of it. Do we know any functions that might work for that? What function, if you take the derivative once, then you take the derivative again, you get back what you started? E to the x would work because you get e to the x and e to the x. Are there any other functions that would work? Cosine and sine as well. So both of those things are true because you can make up a sine or a cosine with e to the x's. But we'll say, okay, sine and cosine. So that means f must be like sine, cosine, some combo of those. G prime over G equals constant. This is the same thing, but now first derivative gives back same function. And maybe a times a constant. Okay, so this one would be the exponential function, e to the x. So G must be the exponential function. Okay, so let's look a little bit at how specifically this could work. So again, a general solution for this. So we don't know exactly what f is going to be, so it's going to be some mix of sines and cosines. So we're going to have a sine and a cosine, and we could potentially get some constants out of it. So we'll let f of x star, say that equals C1 times cosine. This is like a funky squiggle thing. This is the Greek C. It's kind of a fun one to say, xi. It's kind of like a backwards 3 with a funky leg to it. Here, let's go and look up. Just so that you're not like, yeah. It's kind of like that. So that's what I'm trying to draw. The squiggly one, not the capital one. So I'm trying to draw that guy. So do your best in your notes. You can probably draw it better than me. It's just kind of a squiggly thing. I don't know how people write letters that aren't like the Roman alphabet. I don't know. It boggles my mind. Like you look at other languages' letters. How do you write that fast and get it legible? I would struggle. Okay, so C. Time, so that's going to be our constant. We don't know what that is. Times x star plus, oh, okay, and it could be sine 2. So C2 sine C x star. Okay, so this is our function f. Again, it's just kind of a generalized function. So then f double prime of x star. So the second derivative, our C1 would stay, but we would get, okay, so the first part, cosine, we take the derivative and we get, I always forget this. Do you get negative sign or do you just get sine? Negative sign? You take the first derivative, you get negative sine. So you get negative c, the c pops out, negative sine. Then you take the derivative again and you get back to cosine, but you get another c popping out. So you get C1 c squared cosine c x star plus, and you get the same thing with sine. So you take the two derivatives, you get that constant popping out in front twice. Sine c x, sorry, x star. So the thing that we're trying to look at, so f double prime over f equals, sorry, when we would have, I messed up. Both of these should flip to negative, right? Because we go from cosine to negative sine, and then we end up with negative cosine. So they both end up with negative. So we get this ratio would be negative c squared, which works fine. It's just a constant. So now we need to pick a function g where now choose g of t star so that g prime over g equals negative c squared. So that these two things, so that this is also equal to a constant, and it just so happens it's equal to the same constant. That would be our solution. So we already said this is going to be an exponential, but we needed an exponential so that when we take the first derivative, we get an extra c squared in it. So we let g of t star equal e to the minus c squared t star, so that g prime of t star equals minus c squared e to the minus c squared t star, and g prime over g equals minus c squared. Okay, so our function theta is these two things multiplied by each other. So we have like two independent things. One that's controlling kind of how temperature changes with position. That's the F. And one is telling us how temperature is changing with time. That's G. So theta star equals exponential minus c squared t star times c1 cosine c x star plus c2 sine c x star. So that's our answer. Now we have an answer with 3 unknown constants. Lucky for us, we have 1 initial condition, 2 boundary conditions. We have 3 conditions that we already know. So now the challenge is, okay, use those initial conditions, boundary conditions to figure out the unknown values. So we're going to figure out C1, C2, and C. Not C, but C. It's a hard one to say. Okay, so now we can use those to find to find C1, C2, and C. Okay, our first boundary condition, well, you start with boundary condition 1. You can do these in any order, but I'll do it in an order that simplifies things a little bit. So this first one tells us that d squared theta dx squared evaluated at x equals 0 must equal 0. So if we look at our equation, how does that simplify it? So if we take the first derivative with respect to x, it's going to flip this guy to a sine with some constants. It's going to flip this guy to a cosine. If we evaluate it at x star equals 0, sine of 0 is 0. Cosine of 0 is 1. So this guy is going to, this term here, the second term, is going to be still alive, which can't happen because it has to be equal to 0. So the way for that, this tells us that C2 C2 must be equal to 0. So we have to kill that term off. So the way to do it is just to say C2 equals 0 and kill off the whole term, which is nice because now we don't have like 3 functions. We kind of just have 2. So now theta star equals exponential minus c squared t star. We'll write it like this because the C1 can come out in front. Cosine C x star. Okay, we'll use our second boundary condition. In our second boundary condition, we have d x star evaluated at 1 equals minus the BO number times theta star. Okay, so how would that look? You get another page. Okay, so what would that look like? That would give us that minus the BO number times theta star would be equal to, should be minus C times C1 times the exponential of minus C squared T star times the sine of C times 1. But remember, theta star has, right, theta star is all of this. So let's look at what the differences are. So we have a BO number on the left side. We have a negative C on the right side. So this tells us, again, that now we would have that the BO number would be equal to C. In this top term, we have a cosine. In this bottom term, we have a sine. So we're going to have a sine C over cosine C. I apologize, my C is getting uglier, which is just equal to C tangent of C. So this is kind of a weird one. There's a problem. we can't analytically solve this. And there are infinite answers to that equation, right? So BO equals C tangent C. We have to solve that equation. And there's not a really good solution, right? Because tangent repeats every 2 pi. Right, just like sine and cosine repeat every 2 pi. Tangent repeats every 2 pi. So we can solve it and we'll get a new solution for this equation every 2 pi. Which is a little unfortunate because that means we have infinite solutions to this thing that we wanted just one solution for. We can't solve it analytically, like we can't algebraically rearrange it and get a C equals some equation. So the only way to solve this is to solve it by guess and check, to solve it numerically. So we have to solve it numerically. And we get an infinite number. Both a little bit sad. But let's say we got solutions. We can get solutions. But now we have infinite solutions. So we went from having just 2 constants defined to now having an infinite number of constants defined, which is, right, going in the wrong direction a little bit. From n equals 1 to infinity of Cn times the exponential of minus Cn squared T star cosine Cn x star. Where Cn is what we called an eigenvalue. So that's why we used this weird variable to denote what it is instead of just C. It's an eigenvalue of the problem. You've hopefully heard the word eigenvalue before. So it's going to be the positive nth root of this formula equals BO. So C1 is going to be the first positive root of that equation, the first value that solves it. C2 is going to be the second one that solves it. C15 is going to be the 15th value that solves it. So it's going to get solved. This is, for solving it, this is a fairly important point. Occurs between 2n minus 3 pi over 2 less than Cn, which is less than 2n minus 1 pi over 2. Okay, so what does that mean? So for the first one, The first one occurs, it's a positive root, so the first one occurs between 0, it says negative pi over 2, but we can't go negative, so first one occurs between 0 and pi over 2. The second root occurs between pi over, or 3 pi over 2, 1.5 pi, and 2.5 pi. The next one occurs between 2.5 pi and 3.5 pi, and 3.5 pi and 4.5 pi. So basically every solution is spaced, they're not spaced evenly apart. So what you'll find when you find these, they'll be between those two values, but it's not like you add pi to the value and you get the next one. So they're not spaced evenly. You have to solve for each one individually, but they're between these values. So if you want to get the first root, you look between 0 and pi over 2. If you want to get the second root, you have to look between pi over 2 and 3 pi over 2. So it becomes a little bit of a journey to figure out what actually those roots are. We then would plug that root into, we would find an infinite amount of them, which is going to take a while because we have to solve for each one individually. We find an infinite amount. Then we would plug them into this infinite sum here. Then we would have to go back and use our initial condition to find Cn. And right, Cn is C1, C2, C3, C4, C5, C6, C infinity. So it's going to take a little bit. Luckily, people have solved all this stuff before. So that's one of the reasons why we got it non-dimensional, and we did all that work kind of at the outset because people already have figured out all of these answers. So we find Cn to satisfy the initial condition. So if we had a different initial condition, we would get different Cn's. But if our initial condition is that there's a constant temperature everywhere, so our initial condition was that theta star of 0 and x star initially was equal to 1. This gives us a value of Cn. Cn equals 4 sine Cn divided by Cn equals divided by 2 Cn plus sine 2 Cn. So we get an infinite number of Cn's and we get an infinite number of Cn's. There are two different things. One we have to solve for kind of recursively. One we get a nice, pretty simple exact solution. This second one, this Cn term, is going to kind of be the weighting factor for each of those cosine functions, right? It's going to be, cosine is a squiggle, so it's going to be each of the different terms is going to be a different frequency cosine wave, and we're going to be adding up all of these cosine waves to get the, right? So there's going to be a long wavelength one, a medium wavelength one, a really short wavelength one, a super short wavelength one. So they're all going to be different frequency cosine waves. We're going to be adding all of those together to get our final solution. The super handy thing is that most of the time, only the first term matters. So okay, we don't actually have to find an infinite amount. We just have to find one. And then we say, oh, the other ones, they're small, and we don't have to care. So if we look at y, it's this term here. So that's an exponential decay with time. right? So an exponential decay, it's going to be decaying. The first one is going to have, right, Cn is going to be spaced about pi apart. So the first one is going to be some number around 1.5. So minus 1.5 squared t star. It's going to be a number about 1. So about 1 t star. The second term is going to be 3 bigger. So it's going to be like 4.5. So 4.5 squared t star. That's like 16. So you get minus 1 t star, the exponential of minus 16 t star. That term is going to decay a lot faster than the first term. And it's going to kind of keep building after that. So the third term is going to decay even faster away till it becomes meaningless. The fourth term is going to be even faster. So it is an infinite sum, but the terms decay at different rates. So they stopped mattering. Does that kind of make sense why that would be? You'll see when you go through and solve this, you'll see how that happens. So this is an infinite infinite sum, but at t star greater than about 0.2. Basically, only the first term matters. So higher order Cn terms only matter at short time. So this would be the n equals 1 term. So we'll see that too. If you go to accurately represent the initial condition, we need the infinite sum. To accurately represent a little ways after the initial condition, then we can use a fewer number of terms. So basically, the closer you get to time 0, the more terms you need. Okay, but if we're a little ways away from time 0, then we can start dropping off terms, and we don't have to care that it's really an infinite sum. So we'll pick up with this and do an example problem on Tuesday. It is Thursday today. We're going to pick up with this and do an example problem on Tuesday. But remember, this stuff's not on the exam, which is on Thursday. That's Thursday. So an exam on Thursday. We'll pick up with this on Tuesday. But hope you guys have a great weekend. And we'll see you next week.